Hello, am I audible, Anjalita? Anjalita, am I audible? Hello, Anjalita, am I audible?
Yes, sir.
Okay, okay, just wait. Some of the candidates they enter now. Only electrical, ECE and CSE branch students will enter in this class. Only electrical, ECE and CSE branch students. This class is not valid for mechanical and civil students. Just wait 5 2 to 3 minutes. Ayush Kumar, Ayush Kumar, just wait. Some of the candidates enter. Okay, today now we are starting. Uh, we are studied a new chapter, a new topic. In this chapter, uh, theory of relativity. So the theme of today's class is Galilean transformation. Galilean transformation. So after completion of frame of reference, non-inertial frame of reference, inertial frame of reference like this, we are studying. Just a minute, I have seen, I have shared screen. Just wait. Uh, can you, hello, hello, can you see the
Yes, sir.
screen?
Yes, sir.
Yes, sir. It is visible, sir.
Yes, sir.
Clearly visible, na? Hello?
Yes, sir.
Okay, okay. So in this class, before the starting of this class, again I have repeated some of the uh, theme regarding frame of reference, inertial frame of reference, non-inertial frame of reference, because all these things are needed to know about this Galilean transformation equation. So frame of reference, before in previous 2 or 3 class previously I have discussed about all these things. So the definition of frame of reference is a system relative to which the motion of any object is explained is called frame of reference. There are two type of frame of reference. One is inertial frame of reference and another is non-inertial frame of reference. The definition of inertial frame of reference is the frame with respect to which an unaccelerated body is unaccelerated. It means the body is to be at rest or moving with constant linear velocity. And for non-inertial frame of reference, the frame with respect to which an unaccelerated body is accelerated. Unaccelerated body is accelerated is called non-inertial frame of reference. Now, after knowing the theme of inertial and non-inertial frame of reference, we are study about Galilean transformation. Galilean transformation means here for Galilean transformation there are two cases. Galilean transformation describes here first Galilean will take two frame of reference S and S dash are the two frame of reference whose origin is O and O dash, and all these two frame of reference have two coordinate axes. One is x, another is y, and third is z coordinate axis. For this S frame of reference, there are three coordinate axes for S frame of reference, that is x, y, and z. And similarly, again for frame of as this frame of reference, again Galilean will take three. Just a minute. Uh, Three coordinate axes x dash, y dash, and z dash. So here the velocity of this frame of reference, as this frame of reference is movable. In previous class we have already know the one frame of reference is fixed, that is S frame of reference is fixed, and another frame of reference as this is moving with a velocity v with relative to this S. Now just a minute, one has the here this frame of reference is moving with a velocity v with respect relative to this frame of reference S, and the velocity is v here given. Suppose x, y, and z, and x dash, x, y, and z, and t with the time taken by the movement of the frame of reference S relative to S. Here I have written v into t, S equal to v into t. So again I will repeat x, y, z, and t for this frame of reference. These are the coordinates, and time I have told time t at any event in this frame of reference S. For S dash frame of reference, the coordinates is x dash, y dash, z dash, and t dash. T dash be the time taken by this frame of reference S dash. Now x and x dash, here look here, x and x dash axis both parallel to the velocity v. Here velocity v is given here because this frame of reference is moving with a velocity v. So this frame of reference as this axis, x and x dash axis both are parallel to velocity v. Y dash, here y dash and z dash axis are parallel to y and z respectively. According to this figure, we can say that this x and x dash axis, both the axes are parallel to velocity v of this frame of references. Now here y dash and z dash, here y dash and z dash axis of s dash frame of reference. Just a minute, Ritav Chaudhary, Abhay Gupta. Y dash and z dash axis be parallel to y and z axis of this frame of reference S. Let count t from the instant at which the two origins of coordinates O and Y dash coincides. We have to count the time from the instant at which the origin O and OD. Starting of this class, I have told here O and OD with the origin of this frame of reference S and S dash. So let count time from the instant at which the origin of the coordinates O and O dash. So in the direction of this x-axis, look my cursor. in the direction of this x-axis, frame S dash is separated from S by a distance of Vt. The distance between these two frame of reference is S. So if the frame S dash is moving with a velocity v and it takes time t, so with respect to this frame of reference S, so the total distance is v into t. So according to this, we can say that in the direction of x-axis, frame S dash, this frame of S dash is separated from S by a distance of Vt in time t. So coordinate axis x, y, and z for S frame of reference. Coordinates x, y, z, and t time taken for this frame of reference time t of any point in space. Here, suppose here in space, there is a point, suppose here. With respect to this frame S dash and coordinates x dash, y dash, and z dash with respect to S dash frame of reference can be related by this equation. X dash is equal to x minus b. X dash, x dash here, x dash means for this x dash axis is equal to x for this frame of reference x, distance is x minus b into t, the distance between these two frame of reference. Why? Because x dash, x and x dash here x dash frame of reference is movable, so we can use, we can change only x dash axis here part, this part x dash. X dash, the value of x dash will be changed, and the value of y dash, z dash, and t are same with respect to as usual for the frame of reference S. So here, here we can write this x dash is equal to x minus this bt, minus b into t. For y dash, for S dash frame of reference, y dash is equal to y, because in both are parallel. Z dash is equal to z, and we can write again t dash is equal to t. All these equations are getting when the second frame is moving here, means S dash frame is moving relative to first first frame of reference S, here first along positive direction of x-axis. When this frame of reference S dash is moving along the clockwise direction x-axis, relative to, with respect to the frame of first frame of reference S, then these four equations, means equation 1, 2, 3, and 4 we are getting. Again I will repeat all these things. After completion of this, we are going into this. Here there is a point P. Here there is a word coming, space. Word space is coming in this figure. So space means here suppose a point P. So first again I will repeat this diagram. Galilean transformation equation. Galilean has taken two frame of reference. One is S frame of reference and another is S dash frame of reference. S frame of reference is fixed and S dash frame of reference is movable. For this, for case one, means when the second frame is moving here, S dash frame is moving relative to frame S dash, first frame S, in the direction of x-axis. When this frame of reference S dash is moving in the direction of x-axis relative to S frame of reference. So according to this, we can write here S and S dash are the two frame of reference, and O and O dash be the origin of these two frame of reference. Now velocity of S dash relative to S frame of reference, V, suppose V. Here X for first frame of reference, X, Y, Z and T are the coordinates for second frame of reference S dash. X dash, Y dash, Z dash and T dash with the coordinates and time at any event in the S and S dash frame of reference. Now X and X dash, here look my cursor, X and X dash be the axis parallel to the velocity v. The velocity v means here this axis x axis given here, and the frame of reference as this is moving with a velocity b towards this axis. Towards this axis means relative to this axis, x or x dash axis. So, again we can say that y dash and z dash axis be parallel to y and z axis of first frame of reference. Let we have to count time from the instant at which the origin of coordinates O and O dash coincides. O and O dash coincides. So in the direction of this x-axis, frame S dash is separated from S by a distance Vt with a time of coordinates x, y, and z and t of any point in this space here with respect to frame S and coordinates x dash, y dash, and z dash with respect to S dash frame of reference, and it can be followed by these equations. X dash is equal to x dash, we can take in only x dash axis because here s dash frame of reference is movable and it moves with the velocity v. So here x dash is equal to x minus vt, y dash is equal to y for first frame of reference s, means x dash axis we can take in only x dash axis, means its value it changes, and remaining axis are same uh, with respect to the first frame of reference s, means y dash is equal to y and z dash is equal to, here z dash is equal to z, and for this time for this frame of reference s dash if suppose t dash, then coordinate t dash is equal to t with the time for this frame of reference s. All these four equations, 1, 2, 3, 4, are called Galilean transformation. Galilean transformation. These equations are called Galilean transformation, and all these equations are needed in Lorentz transformation. All these figures, 1, 2, 3, 4. These figures are required for Lorentz transformation. Now, another case means case 2. Case 2 states that when the second frame is moving along a straight line relative to first along any direction, it moves in this direction or it moves in anti-clockwise or clockwise. Suppose here again there are two frame of reference S and S dash. The latter moving with a velocity v relative to the forward. We can see again this line. So here we can means this as this frame of reference is moving with a velocity v. relative to frame of reference S. So here again we can write y, x, y, and z are the coordinates and time t. X, x, y, z, and time t with the coordinates of this frame of reference F, and O with the origin of the frame of reference F. Now, again here, there is another frame of reference S dash. S dash frame of X dash, Y dash, and Z dash, and T dash with the coordinates of this frame of reference S dash. So, if these two frame of reference S and S dash, the latter moving with the velocity v relative to the former, so we can write v is equal to a. V is equal to I vx plus j vy plus k into vz. Here vx, vy, and vz are the components of v along x, y, and z for this frame of reference. If this frame, as this frame is moving with a velocity v relative to s frame of reference, then v velocity v of this frame of reference as this v is equal to, we can write I vx for x axis, vx with a velocity along x axis, here x axis, and again jy means j vy with a velocity along y axis, and k vz with the velocity component of velocity along this z axis. Now let O and O dash means O and O dash be the origin of this two frame of reference. So in this two originating points O and O dash, an observer situated at this origin of frame S and S dash respectively, observing the same event at point T. Same event at point T. So coordinate of P relative to O and O dash be x, y, z, t, and x dash, y dash, z dash, t dash. The origin and all these axes, the origin and the axis of the two frame of reference are chosen, so they coincide at t is equal to t dash is equal to 0, means there is no time taken. So if they coincide at t is equal to t dash is equal to 0, suppose from this figure, z axis here, z axis is perpendicular to the plane of paper, this z axis. Then after t time, the frame S dash is separated from S. If this z axis is perpendicular to the plane of the paper, then after t time, the frame S dash is separated from frame S by a distance Vx into t. Similarly, for y we can write here Vy into t, and for z axis we can write Vz into t. So then the observations of the event at this point P taken by both the observers may be seen. Means here there is an observer and O and O dash point. There are two observers are kept. So the observer may be seen by the relation x dash is equal to x minus Vx into t. x dash is equal to here x dash is equal to x minus here x minus v into t v into t. For this v we can write vx into t. For y axis, observer can return y dash is equal to y dash y dash is equal to y minus vy into t. Z dash is equal to z minus vz into t, and t dash is equal to t, because the origin and axis of the two frames are chosen. So they coincide at t equal to t dash equal to 0 here. So according to this diagram, we are observed equation 5, 6, 7 and 8. Case 2. Again I will repeat all these diagrams of case 2. We consider there are two frame of reference S and S dash, the latter moving with a velocity vector v relative to former. So here we can write v is equal to I vx plus j vy plus k vz. Vx, vy and vz are the component of velocity along x, y and z axis. Let O and O dash be the origin of these two frame of reference, and the observer situated at the origin of S and S dash. Look my cursor. Observing the same event at point P, at this point P. So coordinates of point P relative to O and O dash be written as x, y, z into t. For this S dash axis, x dash, y dash, z dash, and t dash coordinates. At this point P, for frame of reference S is x, y, z, t, and S dash frame of reference it can be x dash, y dash, and z dash, and t dash. So the origin here and the axis of the two frame of reference are so chosen that they coincide at t is equal to t dash is equal to 0. T is equal to t dash is equal to 0. Suppose from this figure z axis is perpendicular to the plane of paper, then after t time the framed S dash is separated from frame S by a distance Vx into t, Vy into t. Similarly, we can write Vz into t along x-axis, y-axis, and z-axis. Then the observation of the event at point P taken by both the observers which are situated at these 2 points may be related by these equations. According to case 1, we can write x dash is equal to x minus vt. So here, according to this diagram, we can write x dash is equal to x minus vx into t. This x dash is equal to x minus, in place of vt, we can write vx minus vx into t. For y dash axis, for this diagram, according to this diagram, we are getting equation 2, means y dash is equal to y. But according to this diagram, we can write y dash is equal to y minus vy into t. Vy the velocity component of velocity v along y axis, and it take time t, because S dash frame of reference is moving with a velocity v. Now for z axis, we can write z dash is equal to z minus vz into t, and t dash is equal to t. all these equations means equation 5, 6, 7, 8 are required in required for Lorentz transformation equation. Equation 1, 2, 3, 4 and equation 5, 6, 7, 8. All these equations are in required for Lorentz transformation. Now next is most important uh, uh, for university exam, university question paper. States that Galilean proved that Galilean transformation equation invariance of second law. Prove invariance of second law of Galilean transformation equation. Now, according to we are getting this equation x dash is equal to x minus b into t. So, according to means from equation 1 and differentiating equation 1, we can write dx dash divided by dt dash is equal to dx divided by dt minus b. Here equation 1, x dash is equal to x minus b into t, this equation. And differentiating this equation, we can write dx dash divided by dt dash is equal to dx divided by dt minus here v. So after differentiating, we are getting here equation 9 means dx dash divided by dt equal to dx divided by dt minus b. Again differentiating this equation 9. Again equating this equation 9, we are getting d square x dash divided by dt square dt dash square is equal to d square x divided by dt square. Equation 10. So this equally shows that Newton's second law of motion will have the same form. Newton's second law of motion is in the same form for S and S dash frame of reference. Newton's second law is therefore said to be remain invariant in Galilean transformation. Newton's second law, remember it. Galilean transformation equation obey the Newton's second law. According to this Newton's second law, we can prove the Galilean transformation equation is invariance. So when university exam will ask the Galilean transformation equation is invariance, then in that case you have write all these things. All these things means this part here, diagram 1. Next, its description. After completion of this, you can write this diagram and describe the explanation about this diagram. After completion of all these things, you can write invariance of second law. Only if you have write equation 9 and 10, then you cannot get marks. So you may you write all these things. University question, university will ask that prove that Galilean transformation equation is invariant or it can obey the Newton's second law. Okay, now if anybody have doubt, please ask. Hello.
Yes, sir.
Have, Ayush Kumar, you have any doubt? Ayush?
No, no, sir.
No. Okay, Danish,
Yes, sir.
Danish, you have any doubt?
Yes, sir. No, sir.
No. Just you all wait just 1 week. After 1 week, I will give notes of this theory of relativity chapter. Okay, notes of this theory of relativity chapter. After 1 week, I will give. Muskan Dubey, you have any doubt? Muskan, 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 Neeraj Niranjan, Neeraj, Neeraj, are you audible? Neeraj, Pankaj Kumar Sahu, Pankaj. Hello, Pankaj. Am I audible?
Yes, sir. You are audible.
Yes, sir, you are audible.
There is no doubt. So, okay. Next thing is concept of ether. There is a word coming in previous 2 class, ether medium. There is a word coming ether. So, concept of ether. You know that light waves are transverse in nature, and a material medium is necessary for propagating of transverse light waves. So if the light is propagated into the ether medium, we must expect a change in velocity. Change in velocity. If light is propagated into the ether medium, then we are expected a change in velocity depending on the direction of propagation of light with respect to the motion of the apparatus. Motion of the apparatus means when we are talking about Michelson-Morley experiment. I think Michelson-Morley experiment. In this experiment, Michelson-Morley experiment, we rotate all the apparatus, all the experimental setup rotated about an axis. So remember Michelson-Morley experiment setup. In the explanation about the Michelson-Morley experiment, we are using a word ether. So concept of ether is required for Michelson-Morley experiment only, and it may be used in I think Lorentz transformation also. So ether medium we are using because we can use, because if the light is the reason you have to know, if the light is propagated into the ether medium, we must expect a change in velocity depending on the direction of propagation of light with respect to the motion or movement of the apparatus. Motion of the apparatus, propagation of light with respect to the motion of the apparatus. So this ether what is used? Ether is a medium, not in free space. Ether is a medium, and in this medium, the apparatus should be kept. So you have any doubt? Hello? Hello?
Yes, sir.
Pratik?
Yes, sir.
Yes, sir.
यस हाँ, इसी तरह तुम क्लास में आओ, ठीक है? अटेंडेंस बनेगा,
Yes, sir.
लिंक मिल गया होगा। हम तुमको नहीं भेजे तो हम ये जो है लिख नहीं पाए हैं तुम्हारा कॉपी में, ठीक है? आपको
Oh,
जाएगा,
yes, sir.
ठीक।
Yes, sir.
क्लास में आओ, क्लास में, नहीं तो कुछ नहीं होगा। ओके